Well, hello, folks. I just wanted to do a quick little brief video of helping you with the work that you'll be doing on the scale model of the Earth Moon system. There is an example in the module of doing all of the calculations that you would do for the Earth and the Moon, but using Pluto and its moon Charon as an example with the numbers. So I just thought I'd work through that example. You will need two things really to do this lab. Well, three things. As far as supplies, you'll need some Play-Doh or something like Play-Doh, modeling clay or something like that. And you'll need some string, also a tape measure or a yardstick or something like that would come in handy as well. Right. And you'll need to be able to see the moon, which I would recommend that you do that early. Looks like we'll have pretty good weather leading up to the due date of the lab. So you should be looking at my screen right now that shows the example or cuts from the example that's in the module for the lab, showing you the radius of Pluto, which is 1,151 kilometers. This number pulled out of a textbook somewhere. And then Charon, it's quite large moon, relatively speaking, has a radius of 596 kilometers. Also, we'll need later on that Charon is 19,700 kilometers from Pluto. Right. You will, as part of doing the lab, will get the numbers for Earth's radius, Earth's moon's radius, and then how far the moon is from the Earth. Very different numbers, but you'll use the numbers the same way. So what is talked about in the lab is that the volume of a sphere is 4/3 of times pi times the radius of that sphere cubed, right? But what we're trying to do is we're trying to get the relative size of the Earth and the moon here. And so what we want to do is we want to compare their volume. So the volume of the Earth, using E for that, would be this for the radius of the Earth, and then the volume of the moon would be the same 4/3 pi r cubed, but for the moon, I use an M for that. And we can figure those numbers. They're just humongous numbers, and it's hard to keep track of those big numbers. But what we notice is that the 4/3 and the pi cancel out. And so we can get the ratio of the volumes just by taking the radius of the Earth divided by the radius of the moon, and then cube that number. Right, cube that number like that. And so that's what we've done over here with Pluto and Charon to show you the numbers here. So again, Pluto's radius is 1,151 kilometers. See that right there? We got the 1,151 kilometers for Pluto's radius. Charon's radius is 596 kilometers there. We take that ratio, divide 151 by 596, that gets you 1.93121 and some change. Then when you cube that, again, cubing is not multiplied by 3. It's 1.93 times 1.93 times 1.93. Then you get 7.206. And so round that off to the nearest whole number, like it suggests you do with what you do for our Earth and Moon here. And that'll give you 7. So what that means is when you're doing the Play-Doh work is you're going to make 7 balls for Pluto and 1 ball for, well, you'll do it for the Earth. 7, in this case, I'm doing Pluto and Charon. I would make 7 balls of Play-Doh for Pluto and 1 ball for Charon. I don't want to make them the same size, or just whatever size I'm making them. I'd make a total of 8 balls, because what I figured out is that the volume of Pluto is 7 times larger than the volume of Charon. So what I would do then is I would take these guys and just lump them up into one big ball like that, and have one smaller ball for Charon. And so that would give me 2 objects that have the same scale size as Pluto and Charon. Again, you'll do this with the Earth and the Moon. The Earth's radius, is a lot bigger. The Moon's radius is a lot bigger. You'll get a much larger number than this to kind of get you in the ballpark. You're looking at, let's see if I remember the numbers right, somewhere in the neighborhood of say 30 to 70-ish or something like that. If you get 25, that's too small. If you get 100, that's too big. So something in that maybe 30 to 70-ish range is what you're looking for here. All right. So then you'll make that many balls that you'll use for the Earth, and then 1 more ball for the Moon. Take all the balls for the Earth, crunch them together into one big ball, and you've got a scale model of the Earth and the Moon. All right. The next step in the lab is to try to get those spaced in a scale model of how far apart they are. And to do that, we're going to use the circumference of the planet that we're working with. You'll use the circumference of the Earth. I'm going to use the circumference of Pluto. And then also we need the distance, which if you remember back up here, the distance, the two are away from each other, was 1,970 kilometers, right? So to find the circumference, I'll need for the radius, we've got the radius from earlier stuff that we did. For Pluto, it's 1,151 kilometers. You'll use the Earth's radius for this. So I take 2 times the number pi times that radius, and that gives me the circumference. So 2 pi r gives you the circumference. So in this case, it's 2 times 3.14159. That's our pi. Remember that from the first lab. And then times 1151. That gives me 7,232 kilometers. And I rounded off the decimal places there, right? So then we've got, from there, we've got the distance right here between Pluto and Charon. And so I'm going to take the ratio and divide the distance from Pluto to Charon by that circumference that I just found, right? So you'll do that with the distance from the Earth to the Moon divided by the circumference of the Earth. Now here, when I take the distance of 19,700 kilometers and divide that by the circumference of 7,232 kilometers, I get about 2.72. That's roughly about 2 3/4, right? What I'm going to do is I'm going to take a piece of string and my Pluto ball. You'll do it with a piece of string in your Earth ball and whatever number you get here. And what I'm going to do is I'm going to wrap that string around the ball at its widest point 2 3/4 times, right? And then I either put a mark on it or just cut it to that length. And then when I stretch it out, that distance of that string gives me the space in between the, in my case, Pluto and the Moon. And you'll figure this number out for the Earth and the Moon. Kind of ballpark it here. This is somewhere between like 5 and 25 or so. So if you get 3, then you're way too low. If you get 50, then you're way too big for this distance here. So let's say it's 11. What you'll do is you'll wrap the string around 11 around your Earth 11 times and stretch that out, and then place your Earth and the Moon on either end of the string, and that gives you the distance to the scale for the scale that you made. So one of the things you want to do, since we're doing all this online, is probably just take like a quick picture of that with your phone or something and load that up into the Dropbox so I can see that stuff laid out on the floor or table, wherever it happens to be. The last part, and this is where you need some good weather. We've got the moon up now at this time of the month, so you can use this, but we want to compare what you just did with the size of your models to the relative sizes of the moon as we see it from here on the Earth, right? And we're going to do that by what we call the angular size. And you can look back into chapter 0 of the textbook for more information on the angular size if you like. But let's suppose, I'm just totally making up numbers here just to show you how the numbers would work. But let's suppose that when you did your moon, it had a diameter of 2.4 centimeters. Okay. Now, again, you're going to have to measure that. It's not part of the procedure. Everybody have different size moons. So just take a ruler, just kind of estimate how far it is across the diameter of your moon, right? And then how long was your string? That's how far it is from the Earth to the moon. So what we're trying to compare is how big the moon is to how far it is. And so what we're doing actually is we're looking at having a big triangle. Right? And so let's say for my model, I've got 2.4 centimeters for my diameter of the moon. That. And said, okay, so, and then suppose that is 28.5 centimeters away, right? And so what's this angle right here? Well, that angle in between there, and again, we don't need to get into the trigonometry and all the stuff that would go along with that, but if we want to measure it in radians, which is one way to measure angles, then what we do is we take this side, this long skinny, the skinny side, short side of the triangle, and divide it by the long side of the triangle, the 28.5 centimeters. So I would take 22.4, which is how big my moon is, divide it by 28.5, which is how far they were apart, and 2.4 divided by 28.5 is 0.0842. And again, probably rounded that off some there. And that would be the angle measured in radians. Now, most of us don't think in radians, and so we want to convert that to degrees, like you're using in some of the previous labs you've done. And the way you do that is you multiply this number by 180 degrees and you divide it by pi, that 3.14. So that's where they get this 4.82 degrees. You'll take 0.842 or whatever your number is for your moon and your string, multiply that by 180 and divide it by the pi button or the 3.14159 on your calculator. In this case, with these two, it works out to be about 4.8. In yours, if you're close, spot on, it's going to be somewhat less than a couple of degrees or so. So it's actually closer to a fraction of a degree. And then what's cool is that if you've done this well, what you're going to do is you're going to go out and look at the actual moon. And so I've got a good moon up here in the sky. And change the colors on this. So here's my moon, some craters and dark spots and stuff like that that we can see. And here we are on the Earth. You're going to look and see, all right, what is this and what is this? And because we know, and actually people did this, sorry, my lines won't go straight here. Like that, because people know how far away the moon is, we could figure out how big it is based on the angular size of it here. But what you'll do is you will hold a ruler out at arm's length, and this is where somebody helping you could help. So if you hold a ruler out at arm's length, I'm not going to try to draw a hand, but if you did that, you'd have a ruler here, something like that. And you want to see how much on that ruler does the moon cover up? Does it cover up like 2 centimeters or 3 centimeters or something like that when you hold it out at arm's length? Sorry, let me scare you with a 3D there. And so write that down. And then if somebody can help you, measure from your eye to where the ruler is and get that. And then let's say that this was, say you measured that it was 2.3 centimeters right there. And from your hand out to there, let's say this distance from your eyeball to your hand was a 27.2 centimeters. So then what you're going to do is for the real moon's angular size is do that same process. You'll take the 2.3 centimeters divided by 27.2 centimeters. And I haven't actually done that, but that'll give you the angle in radians. I'll calculate that real quick so you can see how we get these numbers. That works out to be pretty close to what we got out here. It's 0.0846 radians. And if I want to convert that to degrees, then what I do is I take my 0.0846 radians, multiply it by 180 degrees, divide it by pi radians. And that should be pretty close to what we had for the other one. Yeah, so 4.884 degrees is what I got there. All right. Okay. So you'll do something similar with the real moon and with your Pluto moon. All right. Hope that helps. And let me know if you have any questions.